when we charge the cell, anode moving from lithium moving from cathode to anode across the separator. This is the basic of what makes all lithium-ion batteries, whether they're, no matter what the form factor is.
I'm thinking of
and
adding
look at
right
what's
now.
happening today.
I'm not a foam buyer.
I
like adding.
650 form factor to the 21
I like adding
form factor.
on
Great
dip.
collaboration with our partners
And
Panasonic, new partners like LG.
I'm not a huge fan of adding shares. No. I'd much rather play
Actually,
opposite.
slight note on why is the one called 1860?
At this point, what is the price to buy Tesla?
2170 is that
The time to buy Tesla was when
the
we were sitting
the
at
second two-digit
either 21 moving average or 50 moving average
what's up with this weird
for a
number?
very long time.
But
Like
nobody
nobody
explains
explains
to
to
me
me
well.
why. No, because I don't know when you bought. I can't manage your portfolio.
Okay, well, we're deleting the zero that nobody can explain.
My price hasn't been what is priced in the market open. Nobody knows all these, Jack. Nobody knows.
We just got rid of the extra zero. Pointless.
This was
After hours,
an
we'll tell you
evolutionary
when
step,
to open.
going from 1865 to 2170, bringing 50% more energy into the cell. But when we look to the ideal cell design, if we were to do it ourselves, we need to go beyond just what we're looking at is in front of us and study the full spectrum of options. So as you can see, we kind of swept the key figures of merit, how much we can reduce the cost, and how much we
Zabby
can
says
change
Nike's at 131.
the outer diameter of the cell. We found a sweet spot somewhere around 46 meters.
I might sell my Nike at this point.
But it's not just about a bigger form factor. Like anybody can make a bigger form factor.
Any fool could make a bigger form factor.
There
Are we not any fool?
Yeah, exactly. There are problems as you make cells larger. In fact, supercharging and thermals in general become really challenging as you make bigger cells. This was the challenge that our team set our sights on to overcome. And we did. We came up with this tablets architecture that maybe you've heard about that basically removes the thermal problem from the equation and allows us to go to the absolute lowest cost form factor and the simplest manufacturing process. And this is what we mean when we talk about tablets. It's kind of a beautiful thing.
That's what these T-shirts mean. It's very esoteric. Nobody can figure it out. But
yeah. We basically took the existing foils, laser powdered them, and enabled dozens of connections into the active material through this shingled spiral you can see. With simpler manufacturing, fewer parts, 50 millimeter versus 250 millimeter electrical path length, which is how we get all the thermal benefits.
yeah, this is important to appreciate. Like
PTA, you need to calm down.
The
They
distance
ask
that
questions,
electrical
I'm gonna
travel, it's just much less. So you actually have a shorter path length in a large tablet cell than you have in the smaller cell with paths. This is a big deal. So even though the cells
Oh,
are
you're
bigger,
right. For some reason, buying more power with the EMA Tesla
power
over
ratio
time
is
makes
actually
you
better
better
than
money.
the
Yes,
Tesla
for
cell
sure.
with paths. This is again,
At what price do
this
you
is
plan to
quite
buy
hard
it?
to
When
do.
the next time
So,
it is. Until then, I'm playing opposite.
nobody's done it before.
What does FOMO mean? Fear of missing out.
A
That
tremendous
really
value
means
within Tesla
when
engineering,
you're
they're
buying
going to
high.
take your tablet cell and have it actually work and connect that to the top cap, and it's there's a whole bunch of things that we're keeping a little secret sauce here that we're not telling everything.
Honestly, unless you're a mechanical engineer, I don't think
What's
she's
elegant,
going
simple,
to
is still hard.
market.
We took us a lot of
Well,
trials.
it's already up 5% after
Yeah,
hours.
everything's
I don't know
simple
what you're talking
in
about.
recollection. After you it's hard
hard
until it's discovered, then it's simple. So anyway, there's a lot of really cool things going on that enable tablets, and that's really due to a really great engineering team through, and the rest of the team have done amazing work in achieving this tablet construction. And it sounds, I think it may sort of sound a bit silly to some people, but this is like for people that really know cells, this is a massive breakthrough.
For cylindricals to be able to get rid of the tabs, dramatically simplifies winding and coating, and has an awesome thermal and performance benefit.
Yeah, just to elaborate on that, but it's like when the cell is going through the system, it has to keep stopping where all the tabs are.
Yes.
So you can't do continuous motion production if you have tabs. You have to keep stopping, and then there's a rate at which you can start and stop and accelerate again, and really slows down the rate of production. And then sometimes you get the tabs wrong, and you also lose a little bit of active area. It's really a huge pain in the ass to have tabs from a production standpoint.
And so when we put it all together and go to our new 80 millimeter length, 4680, we call this new cell design, we get 5 times the energy with 6 times the power and enable 16% range increase just form factor alone.
Yeah, so these it's pretty great. And just to clarify that when we see these plus 16% or whatever the percentage rate increases, these are the amounts due just to that particular innovation.
Yes.
So we'll list a whole bunch of innovations, and then when you add them up, you get a total improvement in energy density and cost. But these numbers are what refer to just this thing.
Yeah, and I want to stress, this is not just a concept or a rendering. We're starting to ramp up manufacturing of these cells at our pilot 10 gigawatt hour production facility just around the corner.
Yeah. So yeah. It's a video of some of what's going on in the plant.
Oh, they're really trying to get us hyped.
Now, I mean, to be clear, it will take about a year to reach the 10 gigawatt hour capacity. So this is important to appreciate. Like when you build a factory, there's a certain capacity that you design to, and then it takes some period of time to actually achieve that capacity. So I would say it's probably about a year before we get to the 10 gigawatt hour annualized rate with the pilot plant. And this is just a pilot plant. The actual production plants will be more in the order of maybe 200 gigawatt hours, maybe more over time.
And thank you. But let's stack up everything we just saw at the cell level. So just the cell form factor change enables a 14% dollar per kilowatt hour reduction, just that cell form factor change. And now that you've been teased on this factory, we're going to go on and walk step by step through that factory and discuss a series of innovations there. When thinking about the ideal cell factory, we have inspirations behind us in the paper and bottling industry, where from humble beginnings, over a century of innovation has enabled mass-scale, continuous motion, unbelievably low manufacturing costs. And when we think about the lithium-ion industry, which is really only in its third decade of high-volume production, it has so far to go to achieve similar scale and simplicity. And that was the inspiration that we set out to the team as we thought about how to marry cell design and manufacturing in the best possible factory. And let's talk a little bit about what's in a cell factory. First, there's an electrode process where the active materials are coated into films onto foils. Then those coated foils are wound in the winding process we just talked about, where if you do have tabs, you have to start and stop a lot. Then the jelly roll is assembled into the can, sealed, filled with electrolyte, and then sent to formation, where the cells are charged for the first jelly assembled into the can, where the sort of the electrochemistry is set and the quality of the cells are formation. And we set out every step of this process and try to take that inspiration that Sean showed and think about how we make those processes fundamentally better and more scalable process. One of the most important processes is where it all begins, the wet process of the electrode coating. And just to give you all a sense of scale, I'm going to walk through what's in that wet process. You've got mixing where the powders are mixed with either a water or a solvents for the cathode. That mix then goes into a large coat and dry oven where the slurry is coated onto the foil, huge ovens, tens of meters long, dried, and that solvent then has to be recovered. You can see the solvent recovery system. And then finally, the coated foil is compressed to the final density. And when you're looking at this, you're like, wow, That's a lot of equipment for one step, especially when you consider that little speck next to the coating oven. When you're looking at it, like, wow, this is serious iron involved in making that. That's a lot of equipment for one step. Wouldn't it be great, especially when you consider that solvent step, which is one of those dig a ditch and then fill it kind of things where you put the solvent in and then take it out and recycle it. And just go straight to solvent dry mix to coat, which is one of those dig a ditch and then fill it kind of things where you put the solvent in and then take it out and recycle it. In the most basic form, and just go straight to solvent dry mix. You can see it here on a bench top. Literally powder into film. As simple as that.
I mean, it's hard, actually, just to be clear. So, you know, if this was easy, everyone would do it. So it's not like dry coating electrode is actually easy. It's actually very hard to do what appears to be a simple thing. And it's worth noting, like, you know, we did acquire Maxwell like a little over a year ago, I guess. And, you know, it's certainly a good company and everything, but the dry coating they had was like, it's like sort of, I would call proof of concept. Since the acquisition, we've actually revved the machine that does dry coating 4 times. So we're in revision full post-acquisition of the machine. And there's still a lot of work to do. So I would not say this is like completely in the bag. There's still a lot of work to do. And, you know, as you go from like benchtop to lab to pilot to volume production, there are actually major issues that you encounter at every level. It's not like, you know, you make something work on your bench and bingo, now you can make a bazillion of it. It's insanely difficult to scale up.
But if you do scale it up, what you saw before becomes this.
Yeah.
You can see the motivation. A 10 times reduction in footprint, a 10 times reduction in energy, and a massive reduction in investment. But as Elon was saying, simple is hard.
Yeah. Yeah, I mean, to be fair, I would like to say that right now it's just totally working. It's close to working, but it's not, even now at the pilot plant level, it is close to working. Well, it's fair to say probably it does work, but with not a high yield.
Yeah, so we're still ironing out the kinks, but we've made tens of thousands of cells, thousands of kilometers of electrode. I mean, we are on the 4th generation of the equipment, so we've learned a lot along the way.
Yeah.
I mean, it is super demanding because every atom has its place if you want to deliver the energy density and the cycle life and the supercharging.
Yeah.
But we're confident that we will get there, but it will be a lot of work along the way.
There's a clear path to success, but a ton of work between here and there.
Yeah.
So, but this is a really profound improvement. Again, for people that know battery manufacturing, this is gigantic. We'll probably be on machine revision 6 or 7 by the time we do large-scale production. The rate at which the machines are being improved is extremely rapid. Like literally every 3 or 4 months is a new rev.
Yeah, and beyond the electrode, we continue to innovate on every other process step. So let's talk a little bit about assembly, which is next. The key to a high-performing assembly line is accomplishing processes while in motion, continuous motion, and thinking of the line as a highway, max velocity down the highway. No start, stop, no city drive.
Exactly. No stoplights and traffic lights or anything. You want the highway.
You want the highway.
Yeah.
And together with our internal design team that makes this equipment and designs this equipment, we coupled thinking about how to make the best cell with thinking about how to make the best equipment so that we could accomplish the fastest parts per minute rates on all of these tools. And through all of that development, we were able to get to the point where we can implement assembly lines, one line, 20 gigawatt hours, 7 times increase in output per line. And when you're thinking about scalability and pure effort, having one line be 7x the capability is just effort multiplying.
Yeah. So, yeah, you can sort of think about like the sort of the fundamental physics of a factor or something. Like, I think it's actually quite a lot like the rocket equation, where you've got basically in the rocket equation you've got your exhaust velocity and then the log of the start end masses. So it's basically saying, you know, how fast are things going and what percentage of the factory volume is doing useful work. And conveyance does not count as useful work. So
only the value add steps.
Yeah, if you break the factory down into cubic meter sections, and say, or first of all, it would be like 1 meter sections, and say, is a majority of this volume doing useful work? You would be astounded at how bad most factories are. They're like maybe 2 or 3%, including a factory in Fremont. So I think it's possible to get to at least 10 times that volumetric efficiency. So more like 30% ish, maybe more, and be 10x better, which means the factory can be 10 times smaller. And then the other thing is how fast are things going through the factory? It's like speed and density. The faster you go, a factory that's and the other thing is twice the speed of another factory is equivalent to the factory. It's like speed and density. And a company that will be successful is a company that causes that factory and thinks of what other companies take 2 or 3 or 4 factories to do. So this is what we're trying to do here is say, okay, how do we, with one factory, achieve what maybe 5 or even 10 factories would normally be required to achieve?
And the vertical integration with the machine design teams at Groman and Ivar and others allows us to really accomplish that, because we don't have all these edge conditions between one piece of equipment and another. We can design the entire machine to be one machine and remove all of these unnecessary steps.
Yeah, I mean, basically Tesla is aiming to be the best at manufacturing of any company on Earth. This is the thing that's actually most important in the long run. I think, just from a company standpoint and from basically achieving sustainability as fast as possible, but I think also for long-term competitiveness, eventually every car company will have long-range electric cars. Eventually every company will have autonomy. I think, but not every company will be great at manufacturing. Tesla will be absolutely head and shoulders above anyone else in manufacturing. That is our goal.
Manufacturing is hard, and hard problems are fun to solve. Okay, now let's talk about formation. In a typical cell factory, formation represents 25% of the investment. And what is formation? It's charging and discharging cells and verifying the quality of the cell. It turns out we've charged and discharged billions and billions of cells in our vehicles, so we know a thing or two about that. The typical formation setup is you charge and discharge each cell individually. In our car, we charge thousands of cells at once. And we took our principal and our power electronics, leveraging Powerwall, vehicle battery management systems, and others, to dramatically improve the formation equipment cost effectiveness and density. 86% reduction in formation investment, 75% reduction in footprint. You want to take this one?
Sure. So essentially, what this translates to, based on what we know today, is about a 75% reduction in the investment per kilowatt hour, or gigawatt hour. It's just basically 4 times better than the current state of the art to the best of our knowledge. And I think there's probably room to improve even beyond that.
Definitely.
Definitely, yeah. So we're able to, from a volume standpoint, actually get what, in a smaller form factor than Giga Nevada, we were able to get many times the cell output. So you can see, like, basically, we can get a terawatt hour in less space than it took to make a gigawatt hour, 150 gigawatt hours. So this is pretty profound. It's like, I would actually not have thought this was possible several years ago, that we could actually get to terawatt hour scale in less space than what we currently envision for doing 150 gigawatt hours.
Yes, simpler accelerates terawatt hour scale, and that's what we need to do to accelerate our mission. And as Elon said, we're going to try to even improve on this as we push towards our goals, which are.
Yeah. So this is just for. This is just talking about Tesla internal cell production. As I tweeted out earlier, we will continue to use our cell suppliers, Panasonic and LG and CATL, and so this is 100 gigawatt hours supplemental to what we buy from suppliers. Yeah, essentially, this is like reduce our weighted average cost of a cell, because but it allows us to make a lot more cars and a lot more stationary storage. And then long term, we're expecting to make on the order of 3,000 gigawatt hours or 3 terawatt hours per year. I think we've got a good chance of achieving this actually before 2030, but I'm highly confident that we can do it by 2030.
When you look at the size of that factory on the previous page, it really shows how enabling all of these advancements are in achieving a 3 terawatt hour goal by 2030. And not only is all of that manufacturing innovation fantastic for enabling scale, it's also an additional 18% reduction in dollar per kilowatt hour at the battery pack level.
But wait, there's more.
Oh, wait, there's more. Yeah. So we have a manufacturing system, we've got a cell design. What are the active materials we're going to put in that cell design? Let's talk about the anode first. Let's talk about silicon. Why is silicon awesome? It's awesome because it's the most abundant element in the Earth's crust after oxygen, which means it's everywhere. It's sand.
Yeah. Sand is silicon dioxide.
Yeah. And it happens to store 9 times more lithium than graphite, which is the typical anode material in lithium-ion batteries today. So why isn't everybody using it? The main reason is because the challenge with silicon is that it expands 4x when fully charged with lithium. And basically, all of that expansion stress on the particles start cracking, they start electrically isolating, you lose capacity, the energy retention of the battery starts to fade, and it also gums up with a passivation layer that has to keep reforming as the particles expand.
Yeah, basically, with silicon, the cookie crumbles and gets gooey. That's basically what happens.
Good analogy.
Yeah.
And current approaches to solve this, which exist, I mean, we have silicon in the cars that you're all in right now, involved highly engineered, expensive materials in the scheme of things. Now, they're still great, and they enable some of the benefits of silicon. They just don't enable all of it, and they're not scalable enough. And you can see some of the things that maybe you've heard of, SiO, silicon with carbon, or silicon nanowires. I mean, that's kind of the space right now. What we're proposing is a step change in capability and a step change in cost. And what that really is to just go to the raw metallurgical silicon itself. Don't engineer the base metal. Just start with that and design for it to expand in how you think of the particle in the electrode design and how you code it.
Yeah, I'm not sure if you saw this. Basically, $1 per kilowatt hours.
Yeah.
Basically, if you use simple silicon, it's dramatically less than even the silicon that is currently used in the batteries that are made today. And you can use a lot more of it.
The anode would cost, with this silicon, the anode costs $1.20 a kilowatt hour.
Yeah.
And how does it work? Start with raw metallurgical silicon, stabilize the surface with an elastic ion-conducting polymer coating that is applied through a very scalable approach. No like chemical vapor deposition, no highly engineered high capex solutions, and then integrated into the electrode through a robust network formed out of a highly elastic binder. And in the end, by leveraging this silicon to its potential, we can increase the range of our vehicles by an additional 20%, just this improvement.
Yeah, it gets cheaper and longer range.
Yeah, and when we take that anode cost reduction, we're looking at another 5% dollar per kilowatt hour reduction at the battery pack level. And there's more. Let's talk about cathodes. What is a battery cathode? Cathodes are like bookshelves where the metal, the nickel, the cobalt, the manganese, or aluminum is like the shelf, and the lithium is the book. And really, what sets apart these different metals is how many books of lithium they can fit on the shelves and how sturdy the shelves are. Cobalt is a...
Yeah, sorry, I was going to say, it's tough to exactly figure out what the right analogy is to explain cathode and anode, but a bookshelf is probably a pretty good one, in the sense that you need a stable structure to contain the ions. So you want a structure that does not crumble or get gooey, or basically that holds its shape in both the cathode and the anode. As you're moving these ions back and forth, it needs to retain its structure. So if it doesn't retain its structure, then you lose cycle life and your battery capacity drops very quickly.
Absolutely. Yeah, Totally agree. And I think people are always talking about like, oh, what's the cathode going to be? Is it NCA or whatever? You know, the thing to consider is just fundamentally what the metals are capable of, and that's what we have on the chart here. Dollar per kilowatt hour cathode of just the metal, using just LME, you know, London Metal Exchange prices, versus the energy density of just the cathode. And you can see nickel is the cheapest and the highest energy density, and that's why increasing nickel is a goal of ours and really everybody's in the energy in the battery industry. But one of the reasons why cobalt is even used at all is because it is a very stable bookshelf. And the challenge with going to pure nickel is stabilizing that bookshelf with only nickel. And that's what we've been working on with our high nickel cathode development, which has zero cobalt in it. Leveraging novel coatings and dopants, we can get a 15% reduction in cathode dollar per kilowatt.
Yeah. Big deal.
But it's not just about nickel.
Yeah, sure. So in order to scale, we really need to make sure that we're not constrained by total nickel availability. I actually spoke with the CEOs of the biggest mining companies in the world and said, please make more nickel. It's very important. And so I think they are going to make more nickel. But there's also, I think we need to have a kind of a three-tiered approach to batteries. So starting with iron, that's kind of like a medium range, and then nickel manganese as sort of a medium plus, intermediate, and then high nickel for long range applications like Cybertruck and the semi. Something like a semi truck, it's extremely important to have high energy density in order to get long range. So, and just to give sort of iron a bit more time, like although if you look at the watt-hours per kilogram at the cathode level of iron, it looks like nickel's twice as good. But when you fully consider at the pack level, everything else taken into account, nickel is about maybe 50 or 60% better than iron. So iron is a little better than it would seem when you look at it at the pack level fully considered. It's not as good as nickel. Nickel is like 50 to 60% better, but it's actually pretty good. And so, good for stationary storage and for medium range applications where energy density is not paramount. And then, let's say for intermediate, it's kind of nickel manganese, and it's relatively straightforward to do a cathode that's 2/3 nickel, 1/3 manganese, which would then allow us to make 50% more cell volume with the same amount of nickel.
And with very little energy trade-off.
Yeah.
Just enough to have you still want to use 100% nickel for something like a semi-truck, but really not much of a sacrifice.
Yeah.
And, beyond the metals, because a lot of people spend time talking about the metals, actually the cathode process itself is a big target. 35% of the cathode dollar per kilowatt hour is just in transferring it into its final form. And so we see that as a big target, and we decided to take that on. Here's a view of the traditional cathode process. Effectively, if you start at the left and you have the metal from the mine, the first thing that happens is the metal from the mine is changed into an intermediate thing called a metal sulfate, because that's just happened to be what chemists wanted a long time ago. And then when you're making the cathode, you have to take this intermediate thing called metal sulfate, add chemicals, add a whole bunch of water, a whole bunch of stuff happens in the middle, and at the end, you get that little bit of cathode and a whole bunch of wastewater and byproducts.
Yeah, it's insanely complicated. If you look at the total, like if you're just like, it's a small world journey of I am a nickel atom. What happens to me? And it's crazy. Like you're going around the world 3 times. There's like the moral equivalent of like dig in the ditch, fill in the ditch, and dig in the ditch again. It's total madness, basically. And these things just grew up as they're just kind of like legacy things that. It's like how it was done before, and then they connected the dots, but really didn't think of the whole thing from like a first principle standpoint, saying how do we get from the nickel ore in the ground to the finished nickel product for a battery. And so we've looked at the entire value chain and said, how can we make this as simple as possible?
And that's what we're proposing here with our process. As you can see, a whole lot less is going on here. We get rid of the intermediate, metal, water, final product cathode, recirculate the water, no wastewater at all. And when you summarize all of that, it's a 66% reduction in CapEx investment, a 76% reduction in process cost, and 0 wastewater. Much more scalable solution.
Yeah.
And then when you think about the fact that now we're actually just directly consuming the raw metal nickel powder, it dramatically simplifies the metal refining part of the whole process. So we can eliminate billions in battery-grade nickel intermediate production. It's not needed at all.
Yeah.
We can also use that same process we showed on the previous page to directly consume the metal powder coming out of recycled electric vehicle and grid storage batteries. So this process enables both simpler mining and simpler recycling. And now that we have this process, obviously we're going to go and start building our own cathode facility in North America and leveraging all of the North American resources that exist for nickel and lithium. And just doing that, just localizing our cathode supply chain and production, we can reduce miles traveled by all the materials that end up in the cathode by 80%, which is huge for cost.
Yeah, I mean, to be clear, cathode production would be part of the Tesla cell production plant. So it would just be, basically, raw materials coming from the mine, and from raw materials in the mine, out comes a battery.
And on that note, the way the lithium ends up in the cell is through the cathode, so then we should obviously on-site lithium conversion as well, which is what we will do using a new process that we're going to pioneer. That's a sulfate-free process again, skip the intermediate. 33% reduction in lithium cost, 100% electric facility co-located with the cathode plant.
Yeah. So it's important to note that there is a massive amount of lithium on Earth. So lithium is not like oil. There's a massive amount of it pretty much everywhere. In fact, there's enough lithium in the United States to convert the entire United States fleet to electric. Like all the cars in the United States, like 300 million or something like that. Every vehicle in the United States can be converted to electric using only lithium that is available in the United States.
Discovered today.
What we already know is good.
People really haven't even been looking.
Yeah, people haven't been trying because it's just like widely available. So, but it is important to say, like, okay, what is the smartest way to take the ore and extract the lithium and do so in an environmentally friendly way? And we actually discovered again, looking at a sort of first principles physics standpoint, instead of just the way it's always been done, is we found that we can actually use table salt, sodium chloride, to basically extract the lithium from the ore. Nobody's done this before. To the best of my knowledge, nobody's done this. And it's a sort of, all the elements are reusable. It's a very sustainable way of obtaining lithium. And we actually we actually got rights to a lithium clay deposit in Nevada.
Over 10,000 acres.
Over 10,000 acres.
Oh, right.
And then the nature of the mining is actually, I think, also very environmentally sensitive in that we sort of take a chunk of dirt out of the ground, or remove the lithium, and then put the chunk of dirt back where it was. So it will look pretty much the same as before. It will not look like terrible, and yeah, it'll be nice. Nice.
Yeah.
So,
Simply mix clay with salt, put it in water, salt comes out with the lithium, done.
Yeah, it's pretty crazy.
Yeah. So we're really excited about this, and there really is enough lithium in Nevada alone to electrify the entire U.S. fleet.
Yeah, I think that's true. Actually, just what's in Nevada, that's basically there's so much damn lithium on Earth, it's crazy. It's one of the most common elements on the planet.
And eventually, as we said at the beginning, when we get to this steady state 20 terawatt hours per year of production, we will transfer the entire non-renewable fleet of both power plants, home heating and battery and industry heating and vehicles to electric. And at that point, we have an awesome resource in those batteries to recycle to make new batteries. So we don't need to do any more mining at that point. And you can see why. Yeah. The difference in the value of the material coming back from the vehicle versus the ground, you'd always go to the vehicle. And we recycle 100% of our vehicle batteries today. And actually, we are starting our pilot full-scale recycling production at Gigafactory Reno next quarter to continue to develop this process as our recycling returns grow.
Yeah, I mean, to date it's been done by third parties, but we think we can recycle the batteries more effectively, especially since we know our batteries, we're making the same battery as the thing we're recycling. So whereas like third-party recyclers have to consider batteries of all kinds.
Yeah, and just to think about what this actually means, the recycling resource is always 10 or greater years delayed because batteries last a really long time. But eventually, it is the way that all resources will be made available, and that's why we're investing in this recycling facility.
Abundant resources and recyclable
Long-term,
resources.
new batteries will come from old batteries once the fleet reaches steady state.
Okay, so we just talked about scaling cathodes and recycling.
Is what they're selling us on here.
All of the benefits that you just saw are added to this benefit of a 12% reduction in dollars per kilowatt hour at the battery pack level.
Okay, so
almost at our half the cost goal, but there's one more section.
That's
take it away,
crazy.
Elon.
So 50% reduction.
So there's an architecture
price.
that we've been wanting to do at Tesla for a long time, and we finally figured it out. And I think it's the way that all electric cars in the future will ultimately be made. It's the right way to do things.
This could be the big news. What's the news here?
So it starts with having a single piece casting, or a single piece casting for the front body and the rear body. And in order to do this, we
this is manufacturing.
commissioned the largest casting machine that has ever been made, and it's currently working just over the road at our Fremont plant.
Okay.
We have it's pretty sweet.
That's pretty sweet.
Making the currently making the entire rear section of the car as a single piece, high pressure die cast aluminum. And in order to do this, we actually had to develop our own alloy because we wanted a high strength casting alloy that did not require coatings or heat treatment. This is a big deal for castings, especially with a large casting. If you heat treat it afterwards, it tends to deform. It kind of does this potato chip thing. So it's very hard to keep a large casting to have its shape. So in order to achieve this, there was no alloy that existed that could do this. So we developed our own alloy, a special alloy of aluminum that has high strength without heat treat and is very castable. So that's it's a great achievement of our materials team. In fact, in general, we've got a lot of advanced materials coming for Tesla, that new alloys and materials that have never existed before.
Right now.
So,
I wonder what
you're basically making the front and rear of the car as a single piece, and then that then interfaces to what we call the structural battery, where the battery for the first time will have dual use. The battery will both have the use as an energy device and as structure. This is absolutely the way things are done. In the early days of aircraft, they would carry the fuel tanks as cargo. So the fuel tanks actually were quite difficult to carry. They were basically worse than cargo. You had to kind of bolt them down. It was very difficult. And then somebody said, "Hey, what if we just make the wing tanks? What if we just make the fuel tank in wing shape?" So all modern airplanes, the fuel tank, your wing is just a fuel tank in wing shape. This is absolutely the way to do it. And then the fuel tank serves as dual structure, and it's no longer cargo. It's fundamental to the structure of the aircraft. This was a major breakthrough. We're doing the same for cars. So this is really quite profound. Effectively, the non-cell portion of the battery has negative mass. So we save so much mass in the rest of the vehicle. We save more mass in the rest of the vehicle than the non-cell portion of the battery. So it's like, well, how do you really minimize the mass of a battery? Make it negative. Make the battery non-cell portion of the battery pack negative. It also allows us to pack the cells more densely because we do not have intermediate structure in the battery pack. So instead of having these supports and stabilizers and stringers and structural elements in the battery, we now have a lot more space in the battery because the pack itself is structural. What we do essentially, instead of having just a filler that is a flame retardant, which is currently what is in the 3NY battery packs, we have a filler that is a structural adhesive, as well as flame retardant. So it effectively glues the cells to the top and bottom sheet. And this allows you to do shear transfer between the upper and lower sheet. Just like if you have like a Formula One craft or like a racing boat, and you have carbon fiber face sheets and say aluminum honeycomb between them, this gives you incredible stiffness. And it's really the way that any super fast thing works is you create a basically a honeycomb sandwich with two face sheets. This is actually even better than what aircraft do, because aircraft do not do this. They can't do this because fuel is liquid. So in our case, the batteries are solid. So we can actually use the steel shell case of the battery to transfer shear from the upper and lower face sheet, which makes for an incredibly stiff structure, even stiffer than a regular car. Yeah. In fact, if this was like a convertible that had no upper structure, it would be stiffer than that convertible would be stiffer than a regular car. So this is it's just really it's really major. So it improves the mass efficiency of the battery, and then those castings are also quite important because you want to transfer load into the structural battery pack in a very smooth, continuous way, so you don't put arbitrary point loads into the battery. So you kind of you want to sort of feather the load out from the front and rear into the structural battery. It also allows us to use to move the cells closer to the center of the car, because we don't have the in the top one we've got that sort of all the supports and stuff. So the volumetric efficiency of the structural pack is much better than a non-structural pack, and we actually bring the cells closer to the center, and because they're closer to the center, it reduces the probability of a side impact potentially contacting the cells, because it has to go, any kind of side impact has to go further in order to reach the cells. It also improves what's called the polar moment of inertia, which is that if you think like when there's ice skater, arms out or arms in. Arms in, you rotate faster. So if you can bring things closer to the center, you reduce the polar moment of inertia, and that means the car maneuvers better. It just feels better. You don't know why, but it just feels more agile. So it's really cool. This is really major. Like I said, so 10% mass reduction in the body of the car, 14% range increase, 370 fewer parts. So
14% range increase opportunity.
I mean, I really think that long term, any cars that do not take this architecture will not be competitive.
Not necessarily.
And it's not just at the product level a better product, but in the factory, it's a massive simplification. You saw the part removal. It's casting machines. It's the structural battery pack. So we're looking at over 50% reduction in investment per gigawatt hour, 35% reduction in floor space, and we'll continue to improve that as we make the vehicle factory of the future.
Yeah, so major improvements on all fronts, from the cell all the way to the vehicle.
And in addition to the improvements we just said on enabling additional range and improving the structural performance of the vehicle, it is worth another 7% dollar per kilowatt hour reduction at the battery pack level, bringing our total reductions now to 56% dollars per kilowatt hour.
Yeah.
That's good. That's really good news.
Yeah.
All that money, they can't afford to.
All right, so stacking it up.
Jesus.
We're not just talking about cost or range. We've got to look at all the facets. So range increase, we're unlocking up to 54% increase in range for our vehicles and energy density for our energy products. 56% reduction in dollars per kilowatt hour at the battery pack level, and a 69% reduction in investment per gigawatt hour, which is the true enabler when we talk back about how do we achieve this scale problem here.
Yeah. So I think it's pretty nice that investment per gigawatt hour reduction is 69%. I mean, who would have thought?
Yeah, just happened to happen out that way.
I mean, 0.420%, of course. So what this enables us to do is achieve a new trajectory in the reduction of cell cost. And now, to be clear, it will take us probably a year to 18 months to start realizing these advantages, and probably to fully realize the advantages, probably it's about 3 years or thereabouts. So, it's not like if we could do this instantly, we would. But it's really, I think what this bodes, it just really bodes well for the future, and means that the long-term scaling of Tesla and the sustainable energy products that we make will be massively increased. So, what tends to happen as companies get bigger is things tend to slow down. Actually, they're going to speed up.
And they have to speed up if we're going to accelerate the transition to sustainable energy.
Yeah. I mean, long term, we want to try to replace about, at least 1% of the total vehicle fleet on Earth, which is about 2 billion vehicles. So long term, we want to try to make about 20 million vehicles a year.
But I think it's important to point out that when we talked about 3 terawatt hours by 2030, the problem is a 20 terawatt hour problem. So everybody needs to be accelerating their efforts to accomplish these objectives. Doesn't matter where you are in the value chain, there is a ton to do. You need to rethink from first principles how you do it so that you can scale to meet all of our objectives.
Yep.
Anyone?
Sure.
What does this mean for future?
What does it mean for what does this mean for our future products?
Right.
We're confident that long term we can design and manufacture a compelling $25,000 electric vehicle. This has always been our dream from the beginning of the company. I even wrote a blog piece about it because our first car was an expensive sports car, and then it was slightly less expensive sedan, and then finally sort of a mass market premium, but like the Model 3 and Model Y. But it was always our goal to try to make an affordable electric car, and I think probably like I said, about 3 years from now, we're confident we can make a very compelling $25,000 electric vehicle that's also fully autonomous.
And when you think about the $25,000 price point, you have to consider how much less expensive it is to own an electric vehicle.
Yeah.
So actually, it becomes even more affordable at that $25,000 price point.
Yeah. So we have and extreme performance and range.
So pretty much
and we should probably talk about the Model S Plaid. Yeah, what about that?
$25,000. And you're probably going to get crazy performance for that amount of money. And you're also going to get not just crazy performance, but money back just by having a gap. Long term, if they have what they say they have, Tesla is going to be a company now, right? Long term, Tesla is definitely one company, but I think a lot of people are curious if this is going to change short term valuation for Tesla. If this is going to actually boost the stock prices.
We took the latest Plaid out to Laguna Seca on Sunday.
It's not as
a minute 30, and
crazy
we think
as
probably there's
not some,
another 3 seconds or more to take up that time.
Marketing.
We're confident the Model S Plaid will achieve the best track time of any production vehicle ever, of any kind, two-door or otherwise.
Talk for long term. But short term, you may not appreciate this.
And you can order it now, and it's
we're talking about just dollars and cents. We're talking about
available basically end of next year.
Now, do I think it'll go down? No. I don't think the stock price will go down.
And now we'll move to Q&A.
It's going to explode.
So we'll invite a few people on stage.
Like a lot of people have been thinking based on this talk, because there's no real tangibles just yet. This is more or less a lot of.
This is just a small portion of the team, but
sort of.
It would be great to
proof of concept sort of ideas that they're showing us, saying that they've done something, but they haven't really achieved scale on it yet.
Questions to answer.
And because of that, because they have not been able to achieve true scale,
actually, I don't know how we're getting
we don't know,
actually, I don't know either,
when it's going to pay back, except for the fact that it will probably be long term. If you stick with the company, you're long term, for long on Tesla.
Maybe get out of the car for 2 seconds and yell it at us.
5-10 years.
How do we get any questions?
And personally, I would
okay, wait for the mic.
There are mics.
Then I think that the price is actually going to go down.
Okay, we'll definitely need to give people mics, because otherwise there's no way.
Based on, kind of meeting these reductions. And of course, the numbers are never going to match reality. That's more
All right, we don't pass
likely
the mics
going
out.
to be the case. It's probably going to be under 56.
We don't have a name for the $25,000 car yet.
It's a great question, though.
It's just, it was a pretty cool talk, but don't expect like some crazy, stock price increase. Don't expect some crazy stock price increase.
Yes, we will be
I think what you're
manufacturing
really
cells in Berlin.
I
Yep.
think what you're really going to find is that the stock
Thermal
will go
management
up.
system?
It's just not going to go up to 500.
For homes.
I know some
Oh,
people
you mean
are
like the
thinking
home
that, but,
HVAC?
This week, I've seen the
Yeah,
comments on
that's
Google.
a pet project I'd love
500
to
by the
get
end of the
going
week.
on.
I don't see that.
I don't know, maybe
But I
we'll
do see
start working on that next year.
definitely.
Because I just think
you
this,
know,
man, you
the
could
sort
really
of
make a
bleeding
way
that we
better
saw
home
from
HVAC
Tesla,
system
I don't
that's
see that
really quiet
being
and
the
super
case.
efficient.
Now, people might have calls
super
based
energy
on
efficient,
battery,
and
which
also
might
has like
fail
a
and
a
lower
way
the
better
price
filter,
just
for particles, and
expectations. But at the
yeah,
end of
just
the
and
day,
it works very reliably.
I see the price going up
we've
on
already
Tesla
developed
stock.
that for the car. So the heat
Like I
pump
said, not
in
getting
the
crazy.
Model
You're
Y
not going to see any like
is really
17,
pretty
20%
spectacular.
jump up
I mean,
tomorrow
it's
morning.
tiny, it's efficient.
But it's reasonable to
It
expect
has to last
from
for
Tesla
15 years.
from the amount of
It's got to work in all kinds of conditions.
volatility that it has.
The coldest
I
winter to
could
the
expect
hottest summer.
Tesla
So we've actually already
have
done a
maybe
massive
like
amount of the work
6,
necessary for
7%
really kick-ass
bump up
home HVAC.
in price.
And they can also like stack them. So if you want to
5 to
say,
7% bump up
depending upon the size of your house or whatever, how much you need, you can just basically stack them,
throughout the end of the week.
and just have a very compelling, super efficient home HVAC. And then you can also communicate with the car, and it'll know when you're coming home. So it's like, oh, I need to keep the house cold all day. I just cool it down because I know you're coming home. So the pack can communicate with the car and just like really dial it into when you actually need cooling and heating.
Really effective. Like you
That'd be
can't
great.
convince people who don't understand or care to understand technology or facts or figures.
Hey guys, Eli here from Tesla Owners Club, my Tesla Adventure. Just a quick question. So I'm a huge fan of car camping in my Tesla with my dream case. Like my all-time favorite activity. Is it going to be possible to get climate control to the back of the Cybertruck? Because that would be the ultimate camping machine if we can get all that climate control.
We'll try to do that. Yeah, I agree. That'd be really cool. Yeah.
All right, who's next?
Long time fan. Great guy. Just a question. How does the ice industry look like for in the future?
Well, I don't think there will be an ice industry long term.
Ice industry?
Yeah. I mean, well, I guess there might be like a few things that are like, it's a like curious thing. Like, I mean, there's still like some steam engines made somewhere, but like they're just basically sort of quirky collector's items. I mean, that will be the future of the internal combustion engine car.
Hi, Elon. To your left here in the white Model Y, Ryan McCaffrey from the Ride the Lightning Tesla podcast. I'm curious about Cybertruck. It was interesting to see where you had it in on the battery technology front. I'm sort of curious what you see for it in the production front. Is its volume, trucks are so popular in America, do you see its volume equaling the 3 or the Y in the future? And also, is the were you able to get Tesla is able to legally be sold in Texas as part of the Giga Texas deal?
Well, it's hard to say what the volume exactly would be for the Cybertruck. The orders are gigantic, so we have like, I don't know, well over 500,000 orders. I think maybe 600,000 or 600,000. That's a lot, basically. We stopped counting. So I think there's probably room for, I don't know, at least like a unit volume of like 250 to 300,000 a year, maybe more. Now we are designing the Cybertruck to meet the American spec, because if you try to design a car to meet the global, the superset of all global requirements, it basically, you can't make the Cybertruck. It's impossible. It really is designed for the American market, but this is the biggest market. Our North American market is the biggest market for pickup trucks by far, or large pickup trucks. And then I think we'll probably make an international version of the Cybertruck that'll be kind of smaller, kind of like a tight Wolverine package. It'll still be cooler, but it'll be smaller, because you just can't make a giant truck like that for most markets. Yeah, but it's gonna be great. And I don't know. I think probably we'll be able to sell directly in Texas. We do pretty well right now. it is a bit weird not being able to actually conclude a transaction in Texas, but it's got to be like, a click on a server based in California. So, but weirdly, we can do leasing in Texas, but not selling. But hopefully that'll get cleared up in the future.
Elon, great job with everything that you're doing. Frost Gerber from Gerber Kawasaki. Your team's amazing. What I'm most curious about, these innovations are incredible, but on my drive up here, fully on autopilot for 400 miles, the entire state is brown. And this is ultimately about climate. Has there been some analysis done if all these things are achieved? What will its direct impact be on climate?
Oh God, I want a Tesla so bad.
Well, I mean, I think it will have a very significant impact because it will stop
would that be nice?
the CO2 ppm from growing as it is every year. I should say, I try to view the whole climate thing as a science question as much as possible. Science always question your hypothesis. Is it true? Is it not true? Or assign a probability to a given hypothesis. And I should say that my original interest in electric vehicles predates the climate issue. Just when I was in high school, I thought, man, if we don't figure out electric cars, the whole economy is going to collapse when we run out of oil. So it's like, we better figure out electric cars and sustainable energy, or civilization is going to crumble. And then it was only kind of later that the significance of the climate risk became apparent. We were also able, using tracking and other types of technology, to access a lot more fossil fuels than previously thought, which is, helpful for lowering the cost of gasoline, but it's pretty bad for the total tonnage of CO2 that you can put in the atmosphere. It's now greatly beyond what people previously thought. So, but this is, as we were just going through this presentation, it is a absolutely monumental task to accelerate the advent of sustainable energy. The entire global economy is still, more than 99% dependent on, or roughly 99% dependent on fossil fuels. So although electric cars can get a lot of press right now, they're still, and there's still very few, as a percentage of the total global fleet, is practically nothing. I would say, yes, less than 1% of the global fleet is electric right now. Because of 2 billion cars and trucks and whatnot in use. So there's a massive amount of work ahead, just insane, hard to comprehend how much work is ahead to get the new vehicle production to be sustainable, to massively increase the amount of stationary storage, which is critical because renewable energy is intermittent. Wind and solar is intermittent. Sometimes the wind doesn't blow, and obviously the sun doesn't shine at night. So you've got to have batteries, a massive number of batteries. So
it's hard to measure in direct impact, but it's an experiment that we shouldn't be performing. And the sooner we can sort of end the experiment, the sooner we can kind of move on in a fully sustainable way that is actually lower cost. I think the thing that people haven't fully internalized is once we do get to the 25K car, the ownership cost of that car is incredibly lower than the prior car. And then on the solar side and wind, with the cost of solar and wind coming down, and with batteries coming down with them, the actual cost of energy on the grid is going down. So we're sort of moving towards a sustainable, lower cost future. So there's not really a sacrifice.
Yeah, that's true. It is a false dichotomy to say that it's either prosperity or sustainability. This is often used, by oil and gas to say do you want people to lose their jobs? Do you want lower people's standards of living? Do you want to, make all these economic sacrifices, really, in order to have sustainability? And the reality, as Drew was saying, is that a sustainable energy is going to be lower cost, not higher cost, than fossil fuels.
Hey, Elon, quick question for you, right here in front. First, thanks for having everyone, and is telling your friend the one company to go work for that's going to have the biggest structural impact over the next 10 years at scale, it's probably Tesla. So kudos to everyone at Tesla for what they've done to this point and going forward. The two questions for you, as you've looked at the auto and the storage markets, I know you've talked about it kind of 50-50 long term, but it seems like a lot of the battery cost curve achievements that you presented today really make some of these storage opportunities much more feasible over the next 5 years. And so I guess the first part of the question is, does your calculus upon learning and improving these things change on that 50-50 mix, or is there a role where storage becomes bigger? And then the second part of the question, with all these huge grand visions, who's going to be with Tesla from a corporate perspective accomplishing these things? Obviously, Tesla can't do it alone. But when you look at some of the traditional auto industry or power, et cetera, I don't see a lot of other Teslas.
Well, actually, so there's a lot of companies in China that I think are doing great work with electric vehicles and also with stationary storage. Although we don't see that much in the US yet, but I think probably we will in the future. I don't know. I mean, obviously, we're doing everything we can to encourage other companies to move to sustainable transport, and also, make stationary storage batteries. We opened up, made our patents freely available. We really try to tell these companies, hey, you really need to do this, or you won't exist in the future. But they don't believe it, So I mean, we've talked until we're blue in the face. What are we supposed to do? But we really are hopeful that other companies will also do what we're doing, and that will make the sustainable future come sooner.
From a fundamental market size perspective, like we did the first ground up work to show the size of the market in terawatt hours, and they are roughly 50-50. 10 terawatt hours for transportation, 10 terawatt hours for the grid. And part of that is because the grid batteries, because when you're making a power plant, you're making a large investment, are 25-year assets or greater. If the grid batteries were 10-year kind of things, the grid market would be bigger. But because it's a longer duration asset, they're roughly the same size.
Thinking long term, is there any other segments that this new battery will be able to disrupt or electrify beyond just the initial Model 2 or cheaper sedan, like a boat, boring company loop, plane? Boat?
Where are you, Golly?
Are you there? What's up? Right here.
Okay, great.
It's
like ventriloquism here. It's like we just get the sound out of the speaker and you can't tell where the heck it's coming from.
Yeah, any hints, or is the Model 2 such a big deal because it decreases the cost of transportation that is really the disruption? Or should we get hyped that this new cost curve opens up different vehicle categories like a high passenger density bus, or loop, boat, plane?
And then red.
Well, I mean, there are batteries in limited production right now that do exceed 400 watt-hours per kilogram, which I think is about the number you need for decent range, medium range aircraft. I think our batteries will, over time, start to approach the 400 watt-hours per kilogram range as well. I mean, I think over time we'll see all modes of transport, with the ironic exception of rockets, transition to sustainability, or to electric, basically. On the rocket front, what we're planning to do is about 80% of Starship is liquid oxygen, and we're actually already running a power line to be able to use wind power to create the liquid oxygen. So we're making some decent progress on sustainability on the rocket front, but there's just no way to have an electric rocket, and it's important for the future of life and consciousness that we become a multi-planet species. So got to keep doing that.
Hi Elon,
hello.
Josh Phillips here, retail investor. I have a question in regards to the lithium and nickel industries and the likely price spikes and shortages of high-grade materials the EV industry is likely to see if they don't act fast to address future supply. Tesla have clearly made the right moves that are necessary, but there's a real worry that the potential supply issues and price spikes will create a drag on the rest of the EV industry, and therefore a drag on global EV adoption. What advice would you give to the EV and mining industries to quickly solve this looming hurdles? Because for a sustainable energy future, the spice must flow. Thank you.
Who invited the journalists?
Yeah, indeed. Spice must flow. The new spice. I don't know. I think I'm not sure. I guess we can try to like basically overdo it in cell production and perhaps supply cells to others. But we do see the fundamental constraint as total cell production. That's why we're putting so much effort into making cells and kind of reinventing, trying to reinvent every aspect of cell production from mining ore to a complete battery pack because it's the fundamental constraint. We're not getting into the cell business because we, for the hell of it, it's because it's the fundamental constraint. It's the thing that is the limiting factor for rapid growth. But we could certainly try to overdo it on cell production and perhaps sell cells to others. Although we are going at absolute top speed, so it's like it's not like we're holding it back. But I think like just making really efficient cars and that have low drag coefficient, low rolling resistance, efficient powertrains. I mean, that's kind of what we've done in order to make iron phosphate still have a good range. So the iron phosphate is low energy density solution, but there's while there are some limitations on the total amount of nickel produced every year, there's really no limit on the iron. There's so much iron, it's ridiculous. So you can really scale up iron phosphate, at a raw materials basis faster, more than you can nickel. But yeah.
And just to point out, when we were walking through this presentation, we intentionally separated all the different aspects. The benefits of structural battery apply to an iron-based cathode in the same way they apply to a nickel-based cathode. Yeah. So you get longer range iron-based vehicles, and also the silicon benefit can apply to the iron-based vehicles as well. So we can do a lot to extend the range of an iron-based vehicle, which is why it's a key part of the roadmap going forward. And then I invited Turner up here to talk about what the mining industry can do.
Yeah, diversification on the cathode side is obviously massive, and EVs are all about efficiency. And so for the EV industry, for the vehicle industry, we need to see powertrain efficiency really increase at all other companies matching Tesla powertrain efficiency, so that everyone can have that diversified cathode approach where LFP is used in medium range and even really make a 300-mile vehicle with LFP. And really the goal that we were trying to present here was a model for vertical integration, strategic vertical integration that a lot of different people can do. What we need to see is vertical integration that shortens the process path from mine to cathode. And what we're doing here is novel, and we're trying to push the industry in that direction. So we're presenting a model here that anyone can follow.
Yeah, in fact, if there's anything that you guys want to comment on, feel free to step forward and say something.
I think the key is to be smart about your chemistry choices and your materials choices. Yeah, if you're smart about your materials choices, the spice will continue to flow. Yeah. You don't need to use the same kind everywhere. And it's about strategically planning it out. And for miners, I think we are incentivizing them quite a bit to ramp up their production.
Yeah, and actually we had good calls. Like they're all motivated. I think that they've been sort of sitting back being like, are you going to grow like crazy? And we're like, yeah, we're going to grow like crazy. And then I think this indicates we're going to grow like crazy, and that's what the miners want to hear, and then they'll go make the investments.
So, Elon, this is Ben Limpick. I'm a musician. I was wondering, does Tesla have any future plans to make partnerships with music companies like it has done with 10-cent games or things like that for you guys to actually kind of expand your services for artists and other types of creative people to get involved in, producing content that can be part of the Tesla ecosystem, or so other people that do creative things can get involved with you guys?
Well, we don't. We haven't really thought about that much, but I suppose it's probably something we should think about.
Yeah, I'm back.
We will be providing Tidal on Teslas. So we're providing small music sources that people can choose from, and just generally trying to improve the entertainment experience in the cars. And I think actually, as we go to a more autonomous future, the importance of entertainment and productivity will become greater and greater. I mean, to agree that if you're just basically sitting in your car, the car is fully autonomous and driving somewhere, it's sort of like being in a the car is essentially your chauffeur, and then the things that become important are, okay, well, let's have good entertainment, and if you want to do some productivity stuff, then that actually starts to become much more important because you're no longer spending your attention driving the car. So it will be extremely important in the future.
Should we do some of the say.com questions? Okay. Do the second one.
Yeah. First one, if we have, we're able to make it ourselves, which we'll try to do. We will supply other companies. It's definitely not an intentional effort to be ourselves. If we can make enough for other companies, we'll supply them.
I don't think that
We're trying to do, the right thing for advancing the sustainable energy, whatever that is. So
price tomorrow, some
vehicles are great. We get asked that a lot.
climb to $500, but I do think that
I think one thing that's important to note is that vehicles are great.
From all the technology.
It doesn't, unless you have a power cutoff, like you need
so I
to
think everybody
cut off
that
your main
stopped
supply
by,
to the grid. Otherwise, if
especially if you're a
you
subscriber,
lose power in your house,
stop by,
you'll basically just backflow energy to the grid. So just having a reversal in the power flow does not actually keep the lights on. You need a whole separate system to cut off power to the grid. And I think there's also the case that